In this video, we're going to be looking at head loss, but also looking at a problem that we maybe would have seen in thermodynamics class and been able to solve in thermodynamics class. We're going to be looking at the same problem using the idea of head loss. We'll get the same answers, but the solution process is a little bit different. Just gives us kind of another way to think about these types of problems. So we have the pressure rise across a water pump to 35 psi, and we know the volume flow rate is 500 gallons per minute. So that tells us the change in pressure, and it tells us Q. We also know that the pump efficiency is 80%. That's the efficiency eta, or the isentropic efficiency, as we would say in fluid dynamics, or sorry, in thermodynamics. The basic equation that we're going to use is the head loss equation here. We know delta P, that's 35 psi, and we know Q is 500 gallons per minute. We're going to assume a couple things. We're going to assume, because we're not told anything specifically in the problem, that the inlet and outlet of the pump are at approximately the same level. So the height at the inlet is the same as the height at the outlet. We're also going to assume that the diameters are the same. That's not necessarily going to be true. It may not be true in every case, but we'll assume that it's true in this case. So this would mean that the velocities, the average velocities, are also going to be the same if the inlet and outlet are going to be the same. If we do that, then the velocities are going to be the same, the heights are going to be the same. So what we're left with is this equation, that the head loss equals delta P over rho, or minus 35 psi divided by density. The pump work is the mass flow rate times the head loss of the pump, or really in this case, the head gained of the pump. So this is an important equation. This is equal to the mass flow rate times H, which is, we just said, minus 35 psi divided by rho. The mass flow rate, M, the amount of mass per second, is the volumetric flow rate, Q, times the density. So this simplifies our life a little bit because we have Q times the density times minus 35 psi divided by the density. So the density terms will just cancel out, and we'll get Q times delta P, or Q times minus 35 psi. Now we have a little bit of a challenge with the units. We have gallons per minute, and we have pounds force per inch squared. So we want to change the units a little bit to get the right kinds of units. So we're going to change from gallons per minute. We want cubic feet per second. And if we're going to be using feet, let's get this in feet as well. So let's look at pounds force per foot squared for our pressure, so that we're using feet and seconds and pounds. We can do these unit conversions as I've shown here. What we find is that the work of the pump is 5615 foot-pounds force per second. If we convert that to horsepower, this is minus 10.2 horsepower. This is for an ideal pump. Right, which, again, if you remember back from this class, if you remember back to thermodynamics, an ideal pump is one that has no entropy generation, delta S equals 0. This is one that is ideal, perfect. It's the best that we could do. A real pump is not going to be as good. So it's going to give us the same pressure change, 35 psi, but it's going to take more work to get there. So the efficiency of our pump is equal to the ideal work over the real work. And this tells us that the work of our real pump is minus 12.8 horsepower. The minus comes in because that's work that we're having to put into the system, minus 12.8 horsepower. 12.8 is bigger than 10.2 because this system is only 80% efficient. It means that we have to put in more work than we would have to for an ideal system. Hopefully this gives you some sense of how we can handle pump work or work in systems like this. For a system that's simple like this, this whole process is exactly the same as what we would have done in thermodynamics. The only difference is we only see changes from thermodynamics if these two things change. So if we, for example, don't have the same inlet and outlet diameter, then our solution is not the same as thermal. And that's because in thermal class, we didn't talk about really changes in velocity and stuff in any sort of consistent way. We just looked at kind of in and out, and we have always assumed that these things were true. So when we actually have something like the water speeds up across the pump, that takes extra energy to be able to cause a kinetic energy change as well as a pressure change. So if those things change, then the solution is a little bit different than thermal, although this process would actually still be the same. We would calculate for an ideal pump, and then we could calculate again for a real pump. So hopefully this gives you a sense of how to do some calculations that maybe you haven't done in a while, but then also how to look at them in the framework of head law.